this is a Bridges-2 webinar. We have a series of them every 6 weeks or so. But this is a forum for the Bridges-2 community to learn and share ideas of achievements. You can see, if you follow that link, you will see recordings and slides of all the previous Bridges-2 webinars dating back to, I guess, January of 2023 when we started the series. This webinar will also be is also being recorded, as you noticed, and the recording and all the slides will be available sometime next week. We will let you know when, but that's a frequently asked question, and yes, it will be recorded, and both the recording and the slides will be available. But we're looking for topics and speakers of interest, and either work that has been done, is being done, or that you're planning to do. So please, we would be grateful if you could suggest future speakers, including yourself, and topics, including your own, and just email me at that address. So with that, we're ready to introduce today's presenter, Olexandr Isayev. As you see here, he's a full professor in the Department of Chemistry and has illustrious credentials. And essentially, we'll hear about some aspects of his research today. Then just a word about the logistics. So first of all, we do abide by the code of conduct that we share with Access, which is where most of you guys got your allocations to use Bridges-2. And if you see anything amiss, then just let us know, let me know, and we'll address it. But all of us except Oles will be muted during his presentation. So whatever questions you may have, just type them into the Zoom chat. We will let Oles talk. Some of us here on the BSc crew may be able to address some of the more general questions. But then Oles will finish around 10 minutes before the hour, and that's when he will address the remaining and questions, and maybe some new ones that you guys may come up with that were not in the chat yet. So with that, are there any questions for me? If not, then I'll stop sharing and invite Oles to start sharing.
Excellent. Thank you, Sergio. Hopefully you see my slides now.
Yes.
Excellent.
Nice.
Thank you so much. Thank you for opportunity to speak and share research in our lab in Department of Chemistry at CMU. So the title is Second Generation of AIMNet, Foundational Neural Network for Molecules and Reactions. And before I run out of time, first of all, let me acknowledge all the hard work by the group members here at CMU in Pittsburgh. We are across the street in Mellon Institute, and also, collaboration with, our colleagues at Notre Dame, Purdue, funded by the mostly National Science Foundation through several programs, including the NSF CCI Center for Computer Assisted Synthesis and ONR MURI, and definitely, PSC and Access program for allocations. Now, so we are part of the new CCI Phase 2 Center for Computer Assisted Synthesis. And this is a fantastic group of chemists, synthetic chemists, analytical chemists, data scientists, computational chemists, with the idea is how we can use modern data science technology and robotics to accelerate discovery and optimization of organic synthesis and chemical reactions. And you definitely see some of the bias in my work due to activities of the center. But let me start, and when you stop by and ask a lay person somewhere on the street and ask, can you imagine a chemist? I think we have a problem of the image. in the average mind, chemists, those are strange people mixing liquids, maybe getting some fumes outside. Now, if you Google for stock images, you will get something like that. People mixing colorful liquids. Well, at least they have safety goggles here. And of course, the modern chemistry lab look like this, so fume hood and the benches. But I'm computational chemist, so I am not anything like that. And my office is kind of a messy desk, and we use physics-based and data type modeling to understand chemistry, chemical reactions, and molecular design. And I mean, amazing progress in this field due to number of reasons. So first of all, algorithms, of the methods of computational chemistry, but also hardware, right? And a lot of our simulation are currently run on these chips. So this is the GPUs. And of course, we have a Bridges-2 machine, which essentially been designed to do, traditional HPC and a workflow. And also, there's also interesting conversions between computations and autonomous experimentation and robotics, and therefore, kind of future of science, might be autonomous, but this is the topic for another presentations. So I think Chem has been one of the, kind of few pioneers who use computer to understand sciences, right? So these are probably 60 years of this fascinating work. Can a computer learn chemistry, right? So given molecular structure, can I predict, right? What is the reactivity? What is the spectra? And other properties of molecules. And for those who might not be familiar, this is a field of computational chemistry and chemical informatics, right? So this is a rapidly growing field. Computers getting faster, right? We have new algorithms and, new software. Now this is mostly open source software, accessible to everyone. And the sky is the limit what we can achieve with tools of computational chemistry, right? Design of novel molecules, materials, early stage drug discovery, prediction and computation of properties, spectra, NMR, IR, Raman, interaction of light with matter, computing reaction rate, design of catalysts, accurate property calculation. So all of that is the domain of computational chemistry. Why we can do it? Because molecules and quantum, and I promise this is the only equation in my slides. So this is your time-independent Schrödinger equation, right? So it's a partial differential equation that shows different terms, interaction of nuclei and electron, all those terms. And the problem is a very complex equation, and we typically use numeric approximation and do this calculation on HPC resources. Now, so again, because you cannot solve it exactly for practical systems, if you only took quantum, mechanics, quantum chemistry, so the only of handful approximation, things like hydrogen atom, that can be solved analytically, right? And for more complex system, we have to make assumptions, simplifications, and solve numerically. But nevertheless, we still can get accurate results, and that's why it's used in practice. And of course, of the corner approximation, what's called the Born-Oppenheimer approximation. Hopefully, most of you have seen the Oppenheimer movie, which actually, because of the difference in mass of electron and nuclei, we can decouple degrees of freedom and essentially treat motion of nucleus classically and solve only electron Schrödinger equation, right? So you see the separation of these variables, which leads to ideas potential energy surface and molecular dynamics. And therefore, very standard dilemma in computational chemistry. If I do a simulation, what method should I use? If I think about simulation of proteins, realistic molecules, realistic materials, grain boundaries, thousands or millions of atoms, we typically stuck in the realm of this very approximate, crude, empirical potentials, force fields. But if electronic quantum effects are important, we have to solve Schrödinger equations and use certain approximations. And this is where essentially machine learning can help us. So just to get all of us on the same page, what I will talk about mostly focused on what's called the supervised machine learning framework. Essentially, if you fit linear regressions, you essentially have done supervised machine learning. And the goal of machine learning is to find this magic function f that connects, in our case, molecular features with molecular properties or energies. And the way how you do it, you start with training data. So you have this labeled examples molecules and their energy and the properties. And you find you estimate this function by minimizing prediction error. And then when this function is fitted, you apply it, in some kind of perspective validation on new, never seen before examples. And therefore, if we put all of this together, this is why, the field of machine learning, interatomic potential or atomistic potential is really developing these days, right? So I can put this kind of picture on the left. What I plot on x-axis is the scaling of my computational methods. The n with typically number of electrons, and some kind of metric of accuracy. So the force fields, our crude approximations, are typically linear scaling. But the problem is then they're not always transferable. They may work on one example and may not on another, right? And therefore, you have to climb this ladder and include more and more rigorous electron correlation, right? Maybe you'll go to semi-empirical method or density functional theory. All in my realm of organic molecules, so the couple cluster theory is highly accurate, but you pay the price. It's scaled as 7 order of number of electrons, and therefore machine learning provide the means to scale, to kind of bridge the gap. So ML potentials are typically linear scaling, and they can approach the accuracy of the methods. In many cases, we use density functional theory, and therefore provide this 10 to 100,000 fold speed up, and essentially approximating my ground state energy, this magic function f of molecular coordinates or materials coordinates for that matter, right? And the beauty of neural networks, they're fully differentiable. So you take molecule in, featureize, fit into your neural network, you compute energy, but then you can backpropagate, compute atomic forces, the gradient. You can backpropagate twice, get a Hessian matrix, and therefore you can do all kind of simulation that are typical in computational chemistry. And now I think one of the most important problems that chemists are developing is representation of the structure. Well, this is just a random molecule, organic molecule. As we discussed already, molecules are quantum, so they interact to each other with these fundamental forces, of interaction, things like electrostatic, dispersion, and so forth. Now, we as a chemist typically draw two-dimensional sketches and see the structural structure of the molecule. But on a computer, molecule is typically represented as a graph when you have edges and you have nodes, and the edge encode the chemical bond, and the node would be an atom. And based on this molecular graph, both traditional chemical informatics methods, encode molecular structure as the graph, and traditionally, use this graph to compute various features for downstream machine learning tasks, and hence, and essentially enable this file format that chemists are used. But more in contemporary work, we use neural network to operate directly on this molecular graph, either in 2D or 3D space. And therefore, what we see is essentially like a whole zoo of different graph-based neural network, or more generally 3D point cloud, where the essentially atoms are points in three-dimensional space. And therefore, you probably have seen this graph-based, graph convolutional, message passing neural network, the tensor neural networks. And my lab responsible is in a couple of those architectures, and therefore for this seminar, I'll talk about a couple of our architectures. And let me take kind of a historical approach. So this work started in collaboration with the group Adrian Royberg, University of Florida, and probably the most well-known architecture, ANI neural network, which essentially transferable neural network potential for small organic molecules. And in particular, we were interested in kind of drug-like molecule space. So it represents molecule through this local atomic environment, by the name of the very talented graduate student at the time, Justin Smith. I called them Justin Smith symmetry functions. So encode this neighborhood of the atoms, through this descriptor. We pass the neural network, compute local energy, and then sum them up, compute total energy. So this is kind of visually how it works. Every atom inside the molecule represented by the spheric environment. And through the symmetry function, we encode essentially this atomic neighborhood. And neural networks zoom in on one environment at a time. You compute another environment, and the total energy of the system would be sum of these atomic environments, right? Again, if you're interested in technical details, this is the reference. And therefore, we maintain open source ecosystem called Torch ANI. Obviously, we use PyTorch as the choice of our framework for deep learning. We currently parameterize 7 elements. So those are biogenic elements, the carbon, nitrogen, oxygen, sulfur, and halogens. What I'll show in more advanced architecture, we have more elements. For nerd computational chemist in the audience, we use particular choice of density functional theory. So omega B97M branch separated hybrid functional with triple zeta basis set. And we also have a neural network that been parameterized to DLP, linear approximation to the couple cluster theory. And it allows you to do all kind of typical simulations. Compute geometry, do analytical Hessian, do molecular dynamics, your favorite ensemble. You can do thermochemistry, harmonic, quasi-harmonic approximations. We build tool for conformational search of molecules, shown on the next slide. We have calculation gas phase, continuum dielectric, runs on a GPU, and we also have periodic boundary conditions, and this is the link to the GitHub. So it revolutionized how we deal with small organic molecule in the gas phase. Will not bore you with a lot of statistics and details, but it provides you really accurate access to fast but accurate calculation, molecular geometry, and potential energy surface. So here on the left, kind of molecules with halogens and sulfur, they're traditionally very hard to parameterize with a force field. And if I pick a couple of dihedral angles, I can build this conformational potential energy maps. Left would be ANI, right DFT. None of these molecules were used in the training data, so this is true kind of extrapolation examples. And you see minima, we expect to see minima. You see maxima, we expect to see maxima. And the typical error, 1 to 3 kcal per mole for the full potential energy surface map. Here on the right, also give access to accurate gas phase thermochemistry, and references here as well. Let me show you practical examples. Most of chemical structural data typically record as a SMILE string. The problem with SMILE strings encode to the structure, and often a lot of additional information is lost. For example, what is specific tautomer for this molecular? Is there any stereochemistry? And often stereocenters are not enumerated. So after 3D package, which we wrote in Python, is actually designed to solve these tasks. So it takes SMILEs or an SDF file as an input, and then depending on your settings, it can help you enumerate tautomers, stereoisomers, and then we built a parallel optimization engine to do conformational search and minimization of energies, and then you can end up with either lowest conformer or an ensemble if you want to do some kind of Boltzmann averaging, right? So it uses all of our neural networks, run on a GPU really efficiently. You can use it as a Python library, command line, so it's also highly configurable, so you can record your settings as a YAML and use in various workflows. Let me show quick examples. We went to a database of tautomerization reactions. Think about ketone transformations. So we have a bunch of pairs of SMILE strings. So we use after 3D obtain three-dimensional structure and compute free energy in kind of classic rigid rotor approximation, where the free energy is essentially electronic energy, 0-point energy, thermal correction, and entropy term. And computed that independently with QM, the same level of theory. Here on the left, free energy computed with a neural network, free energy with DFT, R² 0.95, minute absolute error 1.5 kcal per mole. And you can see with the wide range of reaction energies, you get, expected results, but about 100,000 times faster if you run on a GPU. Again, lives on the GitHub, been packaged, been used by academic lab, multiple companies and startup. This link on GitHub, pip install after 3D would do it. And, this work was actually featured on the cover of GCAM, a journal from the American Chemical Society. Now, Justin graduated and went to Los Alamos National Lab. So he extended the same framework toward materials. So this is an example of his paper when he used ANI framework to train potential for aluminum, which essentially enabled multi-million atom simulation of a shock wave propagation in a chunk of aluminum and comparing to experiment, right? So this is a little kind of figure, it shows propagation of the shock wave and, various types of phase changes and reactions inside the aluminum. In addition to aluminum, they also done many other metals, including examples like F elements. A few years later, we actually team up with Justin and his colleagues at Los Alamos again, kind of push this architecture to the limit and try to parameterize reactive ML potential. At this point, it's only 4 elements. This is for CHNO chemistry, and paper been published in Nature Chemistry just a few months ago. And again, weights are released in the GitHub. An idea is that if you ever train or try to fit traditional reactive empirical potential, this is literally like an art. There is only a few groups that know how to do it because this is really, really hard problem. So we were inspired with the idea of ab initio nanoreactor from Todd Martinez group. And we used the nanoreactor idea with what's called the active learning workflow, so learning on the fly, to train transferable reactive potential. What does it mean transferable? We parameterize it once, and then it can be used in a variety of different applications. The idea to train is very simple. We pack a periodic box of small molecules, and we run high temperature molecular dynamics simulation varying density and a temperature. So essentially, we cook molecules and induce chemical reactions. We run many, many cycles until the potential converged. And what we show in this paper, that after training, it enabled wide variety of applications, from carbon nucleation, formation of graphene, various combustion reactions, biofuel additives, and kind of paying homage to original nanoreactor paper, prebiotic kind of Miller-Urey experiment. Again, all of this in the paper, but I'll show you a couple of applications. I think one exciting application is the nucleation of the solid phase carbon, which is what is known experimentally and also through ab initio simulations, that if you take carbon in a high density, medium density, and low density, and kind of run the simulations, they would nucleate in different phases, right? So diamond cubic lattice, typically done high density, high temperature. This is how diamond form in the crust. Kind of medium density carbon results in the graphite layers, and low density carbon kind of fullerene onion-like sheets, right? So the potential was not trained to nano materials per se, but it learns enough to reproduce this part of the solid phase diagram, reliable lattice constants, decent phonons. Is this the best carbon potential? Probably not. But it's transferable enough to enable a variety of applications, at least with the concern with reactivity. Again, we had lots of fun doing combustion chemistry, where you, for example, pack hydrocarbons with oxygen and do essentially fun reactive chemistry, see consumption of oxygen, formation of the combustion products, and kind of monitor the kinetics and products, so forth. Right? So 2017, simple idea, very simple architecture, but I think it's enabled variety of very powerful applications. Now, over the years, we kind of have fun playing with design of various neural network architecture. Kind of analogy is building this Lego blocks, constructing the different architectures. So I will fast forward to 2024. But meanwhile, if you're interested about our choice, why we make certain decisions, I can recommend this review we published a couple of years ago that goes into details, why we choose certain things and why not others. So in 2024, this is the second generation, what's called the atoms and molecule ML potentials. The idea is, if you ever heard about quantum theory of atoms and molecules, Bader theory, and it says that electron density of atoms inside the molecules are in the essentially in the consistence, and that's the analogy, right? So this is more advanced architecture. It in principle transferable to all periodic table, but again, because of the practical purpose and kind of the limited computer resources, we parameterize it first on all non-metal atoms. So there's the 14 elements. Now we have silicon, phosphorus, selenium, boron, arsenic if you cares. So sampled variety different sampling strategies and data sources from various data sets. Now, in contrast to ANI, it now can deal with also charged species. So we can compute ions as well. And now this set of elements allow us also extend organic molecules to element organic systems and kind of more exotic calculations. So preprint is here. And again, pre-trained neural network and calculators and training script available from our GitHub. So AIMNet2, as you can see, a little bit more elaborated architecture. A few key difference. In addition to just purely geometrical descriptors, now we can conditional neural network to molecular, charge, and multiplicity. For example, we can encode the spin states. So now we can encode various metals, describe things like magnetism and other things, because we describe the spin degree of freedom. Very important is this orange blocks. This is what's called atomic embeddings. So those are learnable representation of molecule of every atom inside the molecule, hence analogy to Bader's theory of atoms and molecules, and how to make consistent them. So we use idea what's called the message passing, where we pass messages from one environment to another to kind of inform about our atomic neighbors. It also enables description, more accurate description, long-range interactions. Another thing that enable us to describe more local phenomena, what we call neural charge and spin equilibration. So based on total atomic charge and multiplicity, we can predict spin charges on every atom and basically inform appropriate atomic embeddings. Now, overall energy now have this essentially fully data-driven term, kind of local, semi-local energy. Explicit dispersion, because dispersion in dense differential theory is actually post hoc correction. It's fully analytic, so you just can plug it in on top. So you can use your favorite, Grimet type or TS type dispersion. And since we have charges, we can do explicit electrostatics. So you can directly plug in ULAMS or any favorite MD package and use all the machinery to compute electrostatic energy. So the total energy now is sum of two terms. One is fully data-driven and two physics-based terms where we know how to compute it. Now, with these embeddings, we can do fun stuff, right? You can do projection of those learnable embeddings into 2D. So for example, this is t-SNE projection of those embeddings of various types of atoms. And you can do analysis, maybe heuristic interpretation, what's happening with your molecules. So do you see the clusters of different types of atoms? And as you can see here, they really represent this corner of periodic table, right? So oxygen, sulfur, halogens, and hydrogen closer to halogens, which kind of makes sense from chemist point of view. Now you can zoom in on the cluster, for example, those are carbons. And you can see the subcluster of carbon in different substitution environment, polar, non-polar. And overall, those embeddings are highly correlated with the partial atomic charge. And therefore, hopefully, this can help chemists to interpret some of the results of these simulations. A little bit more about this block, which I think very crucial to the architecture, which we called neural spin and charge equilibration. It's based on an idea which we published a couple of years ago separately, which essentially redistribute charge and a spin in a molecule through data-driven way, right? So traditionally, these things are typically done through physics-based, like QQ, charge equilibration scheme. But we designed the scheme going through a neural network. So kind of qualitative how it's work. So for example, this is a prototypical conjugated organic molecule with electron withdrawing and donating group. So imagine if you attach or detach electron from it. So you ionize it or make cation or anion. If you run DFT, this is what spin density tells you. This is highly non-local effect because of the conjugation. You see this formation of kind of spin wave-like behavior. If you try to predict charges just based on purely geometrical descriptors, you'll get qualitatively wrong results. All charges just smear it out. But using the NSC block and the message passing, what we see essentially correct description of this non-local effect and formation of spin wave-like behavior. And again, if you're interested in technical details, the reference go into all the depth, how this work inside the neural network. What's really cool now, we can play with idea what's called differentiable physics. Now, since our neural network fully differentiable, imagine now we have access to what's called the conceptual DFT theory. This is a very interesting theory of chemical reactivity. It connects various quantity, things like chemical potential, hardness, electrophilicity, various kind of indices as the partial derivatives of the energy with respect to the total number of electrons or varied quantities condensed on every atom. Now, because of the design of architecture, if I go back to now I can modulate different charge and spin states, compute this per atom quantities, and essentially compute all of these indices fully bypassing quantum mechanics, right? So this is a side benefit kind of the, full, because of the neural network differentiability, and it reproduces this quantity very well, despite the fact we never trained to it. So it allows really accurate computation of those reactivity descriptors for downstream tasks and application in reaction predictions. Now, what about performance, right? So for the small molecules, things about, typical drug-like molecules, when run on a GPU, AIMNet is actually a little bit faster than, GFN-FF force fields, because some of the intricacies of PyTorch, when you run it on a GPU, it's actually a little bit slower. But nevertheless, if you run it on a GPU, you can really optimize, for example, hundreds of conformers within a few seconds on a single GPU. In the regime of the large system at fully linear scaling, you can fit hundreds of thousands on a modern GPUs, and you get energy and forces within a fraction of a second. So it's much, much faster than QM, but it's a little bit slower than a traditional force fields. So there's still some work to do to bridge the speed gap. And I kind of think about now AIMNet as this foundation model that would enable us to do diverse applications. Now you can combine it with solvation theory, compute properties. Now you can combine it with traditional hybrid simulations and combine machine learning and molecular mechanics and do things like free energy simulation, protein ligand binding. What I'll show you next couple of slides, calculation for the reactions, but also generative modeling. And because we learned so much about basic chemistry and popular elements, there is no need to start from scratch for your particular application, but you can take AIMNet and there's a little bit extra data, what's called fine-tune for specific tasks. And in the remainder of the talk, let me show you a couple of examples. One example is we team up with structural biologist and crystallographer to help in the refinement of protein crystal structures So the preprint really, literally went last month on the bioRxiv. And the pipeline of protein crystallography is really, really complex. You start from the sample, extract a crystal, do a diffraction experiment, or maybe cryo-EM and imaging, and connect this density map. As soon as you density map, you try to fit your atomic model, so actual atoms and chemical bonds, to match your electron density with atomic model. And this is what's called the refinement step. And this is where we really can make a difference, right? So with this a priori knowledge of the density and certain constraints, of the dihedral angles, bond lengths, scientists typically fit this atomic model to this experimental data as good as possible. And that model makes sense. So typical package called Phoenix that used to refine crystal structure, either X-ray or cryo-EM. So if you do traditional refinement, what is really happening, they use very crude methods to account for molecular interactions. So it's a little bit busy plot, but pay attention to orange and the blue structures. Those are important. So if you do standard refinement, you will get atomic structure in this blue line, and this meshes that would be electron density. What has typically happened, this low level but very important details of interaction, like hydrogen bond, different close contacts, are typically not very well accounted with traditional methods. Now, if you plug it in, AIMNet as part of this refinement scheme, because it's been trained on quantum mechanical data, it really understands all these intricacies of interactions. So it gets you much better quality of the side chain, salt bridges, and overall, this is the orange line, much better fit of atomic density of the model, atomic model to the densities. And now it's been a part of the latest release of the Phoenix, and hopefully our colleagues in structural biology and crystallography will take advantage of the much improvement quality, especially for cryo-EM, if you're interested to push it to really atomic resolutions. Now, in parallel and as part of CCAS, we work into adapting AIMNet for chemical reactions, right? Can we help chemists in solving problem robust localization transition state, finding the mechanistic interpretation of the mechanisms? So here we kind of start thinking it, if we added training data about chemical reaction, this would enable us, do approximate method, things like natural elastic band, growing string methods to find approximate location transition state, do transition state optimization, and finally finding intrinsic reaction coordinates, and essentially connecting transition states with reactant and products. So we kind of now work to enable transferable reactive potential with AIMNet for a variety of different reactions, with the idea of help and speed up localization of transition states. Still work in progress, but let me show one example. So this is what's called the triazole click chemistry synthesis, this Nobel Prize award in chemistry. What I'm showing you here, and again, none of these reactions were used in the training data. This one example of this, what's called the intrinsic reaction coordinate. You go from reactants to products to transition state. The line in the red, this is actually DFT. And you can see that essentially reaction AIMNet mimics it very, very nicely. You see, transition state we expect to see, and we test it on a variety of different reactions. So if you have a keen eye and say, oh, wait a minute, these are quite simple, typically uncatalyzed chemical reactions, and you will be right. So our first venture into do really homogeneous catalysis. So palladium would be the first element. And again, we're very close to release the preprint. But again, with additional extra data, we can add palladium and enable essentially modeling of reactive for palladium catalyzed cross-coupling reactions. Typically, think about your Suzuki coupling reactions. You can do really rapid profiling, finding the transition state, writing different ligands, and see how it affects your mechanistic hypothesis. Again, this is work part of our CCAS center. Just to give you one quick example of one of the reaction step, this is what's called the oxidative addition step. This is DFT versus AIMNet geometries for different type of ligated complexes with phosphine ligands. And this regression plots give you, again, kind of idea AIMNet versus DFT energies for a variety of different kind of commercially accessible complexes. And our typical errors, again, about 2 or 3 kcal per mole. And finally, very exciting, because we have a mean to encode spin state. With additional training data, we can have transferable potential for open state system and enable calculation of reactivity for for molecules in singlet, doublet, and triplet states. So this is a collaboration with some of our industrial partners at BASF. And this example of very important reaction, silated benzopicanol. This is one step of reaction activation in the polymerization reaction. So you see going from neutral to two radicals. So if you ever done this calculation, this reaction have a spin crossing. So you start with a, so this plots here on the left, this is IRC calculation with DFT on the left and with the AIMNet on the right. We typically start with the singlet state and it's going way to up, but in the middle you have the crossing with the triplet states, and and essentially have the crossing. And with AIMNet you will be able to do essentially simulation of both states and computing the essentially the free energy and the barrier height even for that reactions. With that, let me finish and point you a couple of links. So ANI model, again, part of the PyTorch Torch ANI implementation are here. We have a plugins for ANI simulation, ANI for various packages, things like ASC, Atomic Simulation Environment, OpenMM, Amber, NumD, Tinker, LAMPS, and also it's in ADF. AIMNet2, paper still under review. So this is the link. This is the code for the AIMNet. So far, we have only 3 plugins for AIMNet2, ASC, LAMPS, and OpenMM, but hopefully more would come. If you're interested to use some of our data, this is the data sets for the 7-element data set. And with that, thank you very much for your attention, and I would be happy to answer any questions.
Thank you very much, Oles. This was great. So if you look at the chat now, you will see, I think there are like 3 questions that we have left for you to answer. So the first one is from Thomas Kroll about the treatment of excited electronic states.
Okay, great question. At this point, what I show you is ground state. There's no excitations. In principle, we're thinking about an extended. We never had a chance. But when I said singlet and triplet, this is ground state just in paired electrons. This is not electronically excited state. But in principle, I think, yes, it could be generalized for excited state as well.
Thomas, any follow-up questions on that?
Yes, maybe if you could quickly comment on like how you would generalize and if you compare those curves, singlet, triplet crossings with DFT, how can you be confident that DFT gets it right?
Okay. No, yes. So of course, yes. If you compare, if you're on TDFT, whatever problems in TDFT will be embedded. This will not address problems, right? Because every error inside the reference data would be embedded, right? And at least to make a transferable potential, it's unlikely we'll be able to go beyond DFT, TD-DFT. But again, if interested, I wasn't happy to discuss. I am not an expert in excited states, it would be interesting to see. But I think all the machinery to train the models are there.
Okay, thank you so much. This is very interesting.
Thank you. Then we have a question about comparison with MACE. Question from
Excellent.
Wayne. Yeah.
I think since what we have are, I kind of skip the benchmark with another method. MACE is very popular method. However, MACE cannot do charge molecules. You cannot do spin states, and MACE is probably 20 times slower. So dispersion term is probably more or less the same, but otherwise, AIMNet would be orders of magnitude faster and more powerful in terms of that you can do reactivity, you can do charge molecules, you can do spin states. None of that is available in MACE.
Any follow-up, Wayne?
Oh, no. Okay, thank you.
Okay, great. And then we have a question from Alspeta. How does the computational cost of AIMNet scale in practice with the number of atoms?
Linear scaling. This is, think about on the right? This is the number of atoms, 25 to 100,000. This is time to get energy and forces in seconds, right? So 100,000 atoms get you half a second to get energy and forces. For the small molecules, you can also batch. So you can do evaluation of multiple things at the same time. So you get an additional speed up.
Alspeta, any follow-up?
No, thank you.
Thank you. And then Shashi, you see that? Have you used AIMNet for periodic systems?
Yes, we do have periodic boundary condition implemented. In principle, it will work. Our current training data does not have crystals, but it's extendable for molecular crystals. It would probably extendable for inorganic systems. So in principle, you can train on materials project, whatever data set you have in mind.
Shashi, is that?
But we have not tried. That's not direction of our work.
Shashi, is that? You have any follow-on? Okay. Then we have a question from Moin about equivariant symmetry functions.
Great question. I think Gabar and Boris and I in different camps. Energy is invariant function of molecular structure. I do believe that for energy and forces, invariant models are way to go, because equivariant models are, MACE is one of the example of equivariant models, is much slower, right? So you will not be able to train larger data set, your simulation are much slower. However, I absolutely agree. If you're interested, I don't know, in tensorial properties, non-collinear magnetism, things where properties are equivariant, things like, tensorial properties, right? I don't know, piezoelectric tensor, something like that. Then you would need equivariant. But for energy, I'm the camps that you will get everything with the invariant model, and not necessarily the same, not necessarily less data for equivariant model. But again, we have a strong disagreement with the developers of equivariant models on this question.
Any comments, Moin? Okay, great. And then a question from Shafi about the extension to inorganic and inhomogeneous reactions.
In principle, yes, we never tried, but again, we have periodic boundary conditions. So technically, yes, but again, don't have a proof because we never tried.
Mm-hmm. Okay, more questions. You see the one from Sudhakar there?
Okay,
Effects of
effect of
solvents.
solvent. Okay, yeah, great question. At this point, we do have a continuum solvent effect baked in. So things like Cosma or CPCM model. Yes, so we have a model that, upcoming and older models that have a gas phase and with continuum solvent. So absolutely. But we have not tried explicit solvent.
Mhm. While we wait for maybe more questions, Oles, would it be okay if you typed your your email contact email address into the chat? So if anybody wants to continue the discussion afterwards,
Sure.
if you're
Yes,
available to
my
answer.
email there or my CMU is all go in the same inbox. So happy to follow up. And I will make a PDF and send it to Sergio, so you'll have access to all the links. You
Yeah,
don't have
send
to
it
make you don't have to
to.
make print screen.
Thank you. Riaz, do we prefer PDF or do we take like just a PowerPoint?
Yeah, whatever you guys want. Yeah, I'll
Yeah,
send them.
also we'll follow up afterwards, like whatever, because whatever our folks want for posting. But I guess we have maybe time for maybe one or two more questions, if you guys have any. Well, if not, then you all have.
So I have
Here you
one
go.
question,
Yeah.
Sergio.
Yeah.
So the data generation for the training, can you describe that for this AIMNet2?
Yes, it's a 20 million calculation for organic and element organic system. We use Orca, so it's a hybrid DFT and the standard atom-centered basis set, triple zeta. So there's 20 million of them. So this is all my, not exceed, now it's access allocation. So it's quite expensive. That's why we are big users of, Bridges, Delta, Expanse, and all the machines we can get hands to.
And what about the training for the network? I mean,
You mean the time to train? So for 20,
and the process and time and
yeah. So the train, it's a couple of days on A100. It's not terrible.
Okay.
Then finally, and this is the last one, we have a question from Anshuman. How many training data points are needed to train MNet2 when we try to study new systems?
Excellent question. So if you're interested in one specific system, then the data set requirements are very low, tens of thousands, maybe in that regime. That depends on specific system. However, if you're interested in transferability, class of molecules, class of system, it's better. It's much more, it's in millions. The details really specific. What we typically do, we use active learning and we look for uncertainty. And again, depending on ML element, there are some simpler elements like halogens, right? But you have multiple valences, different spin states. The data requirement will be larger because you need to sample more diverse chemistry. So essentially use active learning, never use random dataset selection, and uncertainty guide you how much data you would need for your specific use case.
Any comment, follow-up, Anshuman?
So I have a kind of a related question, Les. So for this, I mean, so this one includes only 7 atoms, right? It doesn't include any transition elements or
Our first transition palladium. So we have 14 all non-metals, and the first metal is the palladium. It's not that it doesn't work for palladium, it's that kind of work we're specifically interested kind of avoids the metals. But I have colleagues and we have industrial partners who actually train those models for various systems with metals, including pesky D metals.
Okay. Thanks.
And you see the very last question down there from Wayne. Notice?
Oh, our Hessians are actually very, very good. Great question. It's enough energy and forces to parameterize the curvature or potential energy surface. So if the neural network uncertainty is low, which means in minima, you will get Hessian with all positive modes. For reactive, what you see example of ARC in the transition states for, click chemistry, for palladium, our transition state have exactly one negative mode which connects. So the quality of Hessian is actually good. You will not get exactly the same, the wave numbers for the modes, but the errors within, I don't know, 10 wave numbers or so.
All right, well, great. So I think let's thank Oles for his fantastic talk. And
Thank you.
again, if hopefully we have seeded some thoughts and discussions. So as Oles said, feel free to contact him directly.
Yes,
And yeah,
happy Friday. Bye-bye.
happy weekend. Bye-bye.